Okay, this is step two, 2015, question 8. Interesting question, for sure. I did this question last night, and it did take me a bit of time, like about 30, 40 minutes. And it was mainly just because of this part two. The part two took me a while just to see what was going on and to just try and understand what to do because there's lots of different ways you can approach it. So, yeah, part two is tricky. This is also quite an interesting paper in itself because there's a question on here, which is an integral question, and Black Pen, Red Pen went over it, and it is quite a hard question. At least the last part's quite hard. I think part one and part two are fairly okay, well, quite accessible. But the last part of this question of that question was quite tricky, and yeah. But this question, it was the least attempted question on this paper, and obviously, therefore, the the average marks on this paper were also quite low. So yeah, let's get into it. So we want to show that we basically want to show. Wait, let me get my pen up. Yeah, we want to show this right here, right? Um, and we've got, I drew it out just to make it a bit more clear, but we've got these two circles in this arrangement, um, and we've got lines tangent to specific points on these circles which intersect at the point P. And that intersection point is also known as the focus of these 2 points. And the focus is basically a point. At that point of the focus, if we draw a straight line diagonal, it will go through both of their centers, x1 and x2. It's kind of like a line of centers, sort of. But yeah, and we've got radiuses of this is r1, and this here is r2. Now you might already be able to spot that they share a common angle, right? Both r1 and r2, the triangles they make with this hypotenuse here, which is the dotted line, they both have the same angle. So therefore, they're similar triangles, right? And one way we can kind of go further into this is we can say that this, because they subtend the same angle with this tangent line, or the hypotenuse subtends the same angle, we can say that the sine theta of this angle for both triangles is the same, right? Because it's literally the same angle. So also another thing is that because we're tangent at these points here, the radii make a right angle with this line, right? It's like this. So therefore, we know that sine theta is equal to opposite over hypotenuse, right? So we can take this further and therefore say that sine theta in this case is equal to, right? So which is equal to r1 over hypotenuse for at least this first triangle, which is also equal to r2. We're going to call this hypotenuse 1, and then r2 over hypotenuse 2, right? Because the two hypotenuses, yeah, if I'm saying that right, are different because obviously one is bigger than the other. But because x1 and xp are two position vectors, the hypotenuses are just x1 minus x1 minus p and x2 minus p, respectively. So because if we have two vectors a and b, the direction, or the vector ab, if we have 2 points here which are a and b, which are two position vectors, ab, the vector between them is just b minus a, right? So here we want to find the hypotenuse 1 is actually just x1p, and hypotenuse 2 is equal to x2p, okay, which is pretty much just p. Sorry, it's the other way around. My bad. It's px1 and px2, which is just x1 minus p and x2 minus p, right? So now we can say, if we go up here, back up here, that sine theta is equal to r1 over x1 minus p, but that's also equal to r2 over x2 minus p. Okay. Now, what I'm going to do, I'm going to take the reciprocal of both sides. So we have 1 over sine theta is equal to x1 minus p over r1, which is equal to x2 minus p over r2. I'm just doing this to make it easier for myself, right? And I'm going to just pretty much now all you have to do is rearrange and make p the subject because we want to find the value, like what p is as a vector. So we get r2 times x1 minus p is equal to r1 times x2 minus p, and therefore r2 x1 minus r2 p is equal to r1 x2 minus r1 p. Now we just group all the terms, so we get r2 x1 minus r1 x2 is equal to r1 sorry, r2p minus r1p, and therefore r2 x1 minus r1 x2 over r2 r minus r1 is equal to p. Of course, I mean, it's not, now we just multiply top and bottom by -1, and we'll get r1 x2 minus r2 x1 over r1 minus r2, because we want it in, we want this thing here. But yeah, that equals p, and we've just shown that, right? It's pretty much just comparing the, because they share a common angle, we just compare their sine thetas and equate them. But yeah, part one, it's not too bad. It's like, it's just, yeah, it's not too awful. I think it's quite easy to get the marks there at least. So for part two, now part two is the tricky bit in my opinion. I'm gonna get rid of all of this just so we can save space, but screenshot if you need to, or just rewatch that part of the video. But yeah, let's get rid of that. Okay, I'm gonna first just note down the information we got from part A, that p is equal to r1 x2 minus r2 x1 over r1 minus r2. Now, what's happened is that we now have got another circle in this arrangement, and we don't know where that circle is. And this really tripped me up because I was trying to figure out where is this circle. Does that have an impact on these on the foci we get, or whatever? And what you end up realizing is that the position of C3 or circle 3 is actually independent of where the focus is going to be, or the position vector of that focus. And I'll show you, right? Like, I originally thought if I get this up here, if I get rid of all of this stuff without getting rid of the triangle, okay, wait. Yeah, if I get rid of all of this stuff here, okay. Now we could have circle 3 here, okay. We can have it here. There are like different places we can have it, but I would say there's 3 main places. It's either to the left of C2, to the left of C1, to the right of C2, or in between C1 and C2, which is here, okay? But what you end up realizing is that it doesn't really matter where you put it, because the position vector you get will be the same. So what I'm going to do, I'm just going to place it here just to kind of make it easier, because for me that makes the most sense, just to place it into the middle. And they say they don't overlap, by the way, right? So these actually should not be touching because we don't know if they touch, but for the sake of this diagram, they're just touching. But just remember, they don't actually touch, or we don't know if they do touch. But yeah, so if we name, in fact, I'm going to make this circle a bit nicer. Whatever, this is the best I can do right now, I'm sorry. But yeah, just imagine this to be a circle, right? In fact, you know what, I'm just going to make that. I'm actually going to try and make this even nicer. Okay, cool. That should do the trick, I think. Yeah, that's good enough. Okay. Put someone like here. Okay, so they're not actually touching, but they're like in the middle. So call this C3, this is C1, this is C2. Now it says the focus of C1 and C3 is Q, okay? Now, like how we did here for part 1, we can just name C3 to have a center of X3 and a radius of R3. So let's just define it here. Let's C3 have center, x3, and radius r3. Okay, so we have now the center and we have the radius, and there's some point q, which will probably be like some point here where the focus of these two circles C1 and C3 is. Okay, so just like how we did earlier, where we compared the angles of the sine thetas, well, the reciprocal of the sine thetas, actually, the reciprocal of the sine thetas of both of these triangles, they subtend with the tangents. We can just do the same thing for C1 and C3, because this will have a radius of R3. By the way, imagine this is tangent. This has to be tangent. This circle 3, but it won't. It'll be quite hard to draw, so I'm not going to do it. But this is R3. This also creates a right angle, and this is C1. Obviously, this is R1, and this also creates a right angle, which has already been drawn. These will both create lines or right angles, these will create triangles, with the focus. So the hypotenuse of the triangle of C3 will end up just being the vector from Q to x3. So it will just be qx3, which is x3 minus q. And for the hypotenuse with the triangle with circle 1, it will be q x1, which is equal to x1 minus q. Okay, I think that just the common trend here is that the hypotenuses are just the direction vectors between the foci and the center of that circle. That's like the main thing. And so if we have the hypotenuses, we have the opposite side. We can just do, I'm going to go straight to doing the reciprocal, which would just be 1 over sine theta is equal to x3 minus q over r3, which is equal to x1 minus q over r1. Now, remember when I said that the position vector is independent of wherever you place it? Now, let's say we got this circle here, right? And we placed it all the way over here. Let's say we placed it here, and we did it like this, right? This is really messy, I'm sorry. And let's say that q was here. It would still be the same thing. We're still doing x3 minus q is equal to x1 minus q, and x3 minus q over this radius here is still equal to x1 minus q over this radius here of r1. You would just end up getting the same thing. It would just come out to be like this. It would still be x3 minus q and x1 minus q. So you don't actually need to know where this specific position of this circle is. It really is just independent. So, or at least the focus or the position of the focus is independent of wherever you put this circle, which is a good rule of thumb. Like if they don't give you the position of any new thing they've added in a question, it usually means the thing they're trying to get you to find is a general sort of rule, or whatever you're trying to find is independent of wherever the location of that new thing is. So it's just a really good thing to kind of keep in mind, and don't let it kind of put you off. Don't let the position of that circle put you off, because it'll be the same either way. But yeah, if you rearrange, you'll get x3 minus q r1 is equal to x1 minus q r3, and therefore x3 r1 minus q1 r1 is equal to x1 r3 minus q r3. And then we can just do that whole thing about kind of not comparing, by making q the subject. So we're going to get q3 r1 minus q1 r3 over r1 minus r3 is equal to q. Okay, so we've gotten q. Let's bring this up here, because we want all of this information. Now we're going to do the same for the foci between C2 and C3. And it's literally going to be the same thing. It will just, it's just going to be, now the hypotenuse will be, because it makes now the focus between them is just r. So it would just be x3 minus r over r3 is equal to x2 minus r over r2. It's just the exact same sort of thing you're doing earlier. Like the ratio between those sides are the same. And again, it does not matter where you put C3 because even if it's here, right, it's still, if r is like, let's say here, let's say r was here, the vector between them is still x3 minus r. Even if C3 was in the middle, like they're here, it would still be x3 minus r. So it doesn't really change, like the whole, it's still just always going to be that position vector of the center minus the focus. So again, if we rearrange, we're going to get x3 r2 minus r2 is equal to x2 r3 minus r3. And again, you would just end up getting x3 r2. In fact, let's just make that nicer. Yeah, x3 r2 minus x2 r3 over r2 minus r3 is equal to r. So again, we're going to put this up here. So we've gotten all of this. So we've now gotten the position vectors of p, q, and r. Okay. But it doesn't just want that. It wants us to show that it's in the same line. Now, the reason we found p, q, and r is to basically show that the vector between, well, okay, if we think about what, I'm going to get rid of all of this, by the way, just to save space. If you think about 3 points on a straight line, A, B, C, all of these are position vectors, right? The vector of AC is just a scaled up value of the vector of BC. So the way we write that mathematically is just AC is equal to lambda BC, lambda AB, sorry, right? Which makes sense, right? If you have like a line, sorry, why isn't this going away? Yeah, if you have like a line like this, right, and we just scale it up, that's all that's happening. We're scaling it up like this. Literally, this is AB and this is AC. This is AB and this is AC. You're just scaling up that line. And you probably know this from like core pure or any sort of A-level maths. If 3 points are in a straight line, you just need to find the position vector of 2 points relative to one of the points, and or not the position vector, the direction vector, and we need to show that it's a scalar constant of the other. So sorry if that's not a great explanation, but yeah, you will see what I mean when I answer the question. But we want to essentially show that PR is equal to lambda QR. Okay, because if these lie in a straight line, this identity will hold true, right? So yeah, let's do it. So if we have PR, that's equal to R minus P, which is just x3 R2 minus x2 R3 times R1 minus R2 minus x2 R1 minus x1 R2 times R2 minus R3 all over R1 minus R2 times R2 minus R3. That's PR. Okay. Now let's take this out, so we get 1 over R1 minus R2 minus R3. Okay. Now here it gets pretty algebraically like finicky, but we just kind of need to like trust the process and just hope we get something good coming out. So first we need to find PR, so we just need to like expand all of this out, and we're get R1 R2 x3 should be clearer. Minus R1 R3 x2 plus R2 squared x3 plus R2. Okay, I've just skipped all of the algebra because it would take me ages. But essentially, you get when you expand everything and you take R2 and R3 common from PR and QR respectively, you get this, right? And you see that this and this is just the same thing. So if we label this thing here f of x, right? Just let equal f of x. Okay, we get R3 over R1 minus R3, R2 minus R3 equals f of x equals QR, and R2 over R1 minus R2, R2 minus R3, f of x is equal to PR. Okay, now because essentially this is our lambda right here, right? This is our lambda. So we've pretty much just shown that QR scaled up equals PR. So therefore, since QR and PR share f of x, then P, Q, R are on straight line. Okay. Yeah, quite a long question because of expanding out the algebra, I'm probably gonna cut out some of that, like edit out. But yeah, yeah. So that's literally it. Like that was the part two. I think this was the hardest part of the question. Part three is quite simple actually, because we just need to show, we just need to find a condition for R1, R2, and R3 that Q is the halfway point between P and R. So I'm gonna cancel out all of this, right? I'm gonna cancel out all of this working here, just again to save space, right? Delete. I'm gonna bring this up here. Actually, I'm gonna delete all of this as well, and I'm gonna cut all of this. Sorry, it's really messy, but the best I can do right now. Just bring this up here. Okay. So we've gotten this, right? We've got this, and we now need to find a condition that Q is the halfway point between P and R. Now, if you think about it, right, if Q is the halfway point between P and R, then and we know that this is true, then lambda just must equal 2 here. So we need QR, 2QR must equal PR. Okay, therefore 2 times R3 times R1 minus R3 of R2 minus R3 must equal R2 over R1 minus R2, R2 minus R3. Okay. Now this here can just cancel out, right? So then we get this thing happening. We can just do some expansions, and we get R1 minus R2 equals R2 R1 minus R2 R3. And we get 2 R1 R3 minus 2 R2 R3 minus R2 R1 minus R2 R3. We get this the other side, so we get 3. We get 2 R1 R3 minus we get that to the other side, which is R1 R2 R3 is equal to R2 R1, and then 2 R1 R3 is equal to R2 R1 plus R2 R3. And yeah, that's our condition. That is literally the condition for this to hold true. That's literally it. That's like the whole question done. Yeah, interesting question for sure. Let's go to the examiner report and see what the examiners saw to be difficult in this question. Okay, so let's get rid of that. This was one of the least attempted questions on the paper, and the average score for the question was quite low. Yeah, that makes sense. It does, like, if you look at this, you're like, what the hell is happening? What the hell is this? What the hell is this? And also, if you can't get part one, you're cooked, right? Like, you can't get part two and part three because they follow from the same sort of concept, because you need to find Q and R, right? So it doesn't. It's not that. It's one of those step questions where part two and part three aren't accessible without part one. Um, Part one was answered correctly by the majority of candidates. Yeah, that makes sense. But part two was approached in a much more complicated manner than necessary. Okay, yeah, that also kind of makes sense, because when I saw the question and I did it originally, I was like, okay, my first issue was where to place C3, and then my second issue was like, I I thought of trying to find a way of expressing x3 in terms of x1 and x2, because x3 wasn't defined here. They didn't tell us what that we needed to even consider x3. But you realize you can't really do that, and the main reason you can't do that is because you don't know the position of C3. Because if you want to write x3 as a function of x1 and x2, you need to know the position of C3, because it's dependent on that, right? Like, it would be different if it would be different if it's in between. Oh my god, I can't speak. It would be different if it's in between C1 and C2, right? But but if it's to the left of C1, then obviously the position vector would be different because it's relative to x1 and x2. And likewise, if it's to the right of C2. So you can't really express x3 in terms of x1 and x2. And if you try and do like more lambdas and more scalar constants, you just end up getting a really messy thing. So your best bet is just leaving it in terms of x3 and r3, and then just hoping when you compare the lines, right? Because you're only focusing on X, P, Q, and R, and those points specifically. So it doesn't matter what R3 is. You just need to show that you get the same function inside this bracket, so the same f of x inside the bracket. So yeah, but it makes sense why people were trying to do different, more complicated things. Where the vectors were considered, solutions could have been made clearer by grouping the terms. Yeah, to be fair, I could have made my brackets clearer. A number of solutions referred to the division of vectors rather than comparing coefficients. Oh. Okay. It seems as if just the main issue was that people took this question and just didn't really know how to express the straight line bit, and they were trying to do more complicated methods than necessary, which makes sense. Yeah, I think this question is quite, like, there are multiple ways to approach it, but I think this is the easiest way to approach it, even though this question still isn't easy by any means. But yeah, that's it. If you guys have any other questions you want me to go over, write them in the comments. I'll be doing an induction question probably soon from the 2015 paper. The only issue is the part B of that question I'm not too sure about, so I need to try and see if I can figure that out. But other than that, yeah, thank you for watching. Again, any other questions, just listen in the comments. And yeah, thank you. Bye bye.